Hi, I'm Shaul. In this video, I would like to share with you some revelations about the relations between optical design and true-to-life rendering of a lens. I hope you find it useful, or at least interesting. Now, in the previous video, I set out to test the rendering of six short telephoto lenses in the focal ranges of 55 to 58 millimeters. I find this type of focal length quite useful for portraits for reasons I explained in the previous video. Anyway, I took a series of portraits, sadly non-identical ones, of one of my friends, and put up a survey in which I asked you to rate the rendering of each lens on a scale that goes between 1 and 5, where 1 signifies a flat rendering and 5 signals a true-to-life rendering. Looking at the results of this survey, none of the lenses that took part in this test was entirely flat, but still there was quite a range of perceptual lifelike rendition between those lenses. So let me start by the winner of this test, and that is this old little thing, the Helios or Gelios 44 M6, which is a relatively recent version of this lens, made in the late 80s and the early 90s. Now, the photograph taken with this lens got an average score of 4.08, where all respondents, or 100% of the respondents, agreed that the rendition was not flat. By that I mean all the ratings were 3 or more. And 77% of the respondents rated the rendition as distinctly lifelike, which means 4 or 5. This lens is known for its swirly bokeh. This is what makes it popular, especially among cinematographers. But it also makes a very deep, true-to-life image, albeit slightly on the lower contrast side. In the second place was this lens, the Nikon 58mm f1.4. It reached an average score of 3.77, where 85% of the respondents agreed that its rendition was not flat, and 69% agreed that it was distinctly true to life. This is a relatively modern lens made in 2013, but it was made with character in mind. It's less than entirely sharp, wide open, and suffers quite a bit of chromatic aberration. The next lens was this one, the humble Autochinon 55mm f1.7. It was a kit lens that was sold in the mid-70s, but its rendering is quite pleasing, it's quite poppy. It reached a mean rating of 3.62, where 77% of the respondents agreed that the rendition was not flat, and 62% rated the rendition as distinctly poppy or true to life. In the fourth place was this one, the venerable Falkland 58mm f1.4 SL. This is an old lens in a modern scheme. It started its life in 2003 and had a few versions, all with the same optical quality. Now, this lens had a mean score of 3.46, where 69% of the respondents agreed that it wasn't flat, and only 50% defined its rendition as distinctly lifelike. That surprised me a bit because it's known to be a highly poppy optic, and it has quite a good reputation amid aficionados of lens character. In the fifth and sixth places in this test, there are two quite different lenses. Both of them scored an average rating of 2.77, which means that they are on the flat side. All the first four lenses had a mean rating of above 3, which puts them on the poppy side, while these two were below 3. One of them was this old lens, the Konica Hexanon 57mm f1.4, which was introduced in the mid-60s. It's one of the oldest lenses in this test. It had a mean rating of 2.77, where 54% of the respondents agreed that it wasn't flat, but only 31% of the respondents defined its rendition as distinctly lifelike. And the last lens is this one, the one I set out to make this test because of the Mikey 55mm f1.8, which was only introduced late last year. It also had a mean rating of 2.77, with 54% of the respondents agreeing that its rendering is not flat, but only 23% of the respondents defining its rendition as distinctly poppy. Despite my hopes that this would be a good poppy lens made for the modern mirrorless mounts, it failed this test. Anyway, according to the opinions of the respondents to this survey. It is not entirely flat like other modern lenses, but it's far from being true to life. The survey allowed me to interpret the rendition of those lenses in a way I wasn't able to do before. First, the poppiness of those lenses is not only based on my own opinion, exclusively used in the past. Now it's a result of public polling, which gives it more resonance. And second, the multitude of data points allowed me to evolve the poppiness rating from a categorical variable into a continuous one, which is much preferred from the statistical point of view. You can do a lot more with those data when you can put them on a continuous scale. As already established on this channel, poppiness or true-to-life rendition depends on refraction and dispersion allowed by the glass in a lens. The more refraction, the more dispersion, the more true-to-life the rendering will be. From an engineering point of view, that depends on the chemistry and the arrangement of glass elements in a lens. The more high refractive index glass, the more poppy the image will be. The more low dispersion or ED glass, the less poppy it will be, the more clinical or flat the image will be. So I came up with a formula or a way to categorize lenses into 4 categories of true-to-life rendition that was based basically on the percentage of ED glass out of the total glass used in a lens. But now, due to the continuous nature of this variable, I was able to develop a mathematical score that can actually predict the poppiness of a lens in a more precise manner. The amount of ED glass elements is always stated by the lens manufacturers in the lens specifications. However, the amount of high refractive index glass is only sometimes mentioned in those specifications. So you have to deduce it. And to do that, you have to look at complex groups, optical groups that contain more than one element. In those groups, it is likely that elements with differing refractive indices are cemented together. So at least one of those glass elements is a high refractive index, which is a good way to estimate the amount of high refractive index glass in a lens. I developed a variable that I call the dispersion score, which is calculated by the number of complex groups in the lens minus the amount of ED elements. You have to divide the results of that subtraction into the total count of elements in the lens. And you get a number that is typically smaller than 1 and higher than -1. The higher the dispersion score, the more true to life the image will look. So I looked at the optical characteristics of each of those 6 lenses and calculated the dispersion score for each one. The order of the dispersion scores among these 6 lenses was exactly the same as the order of the poppiness ratings obtained by the results of the survey. The Helios 44 had the highest dispersion score of 0.33, while the Mikey had the lowest dispersion score of 0.09. Then I fitted the curves that showed the relations between dispersion score and the average ratings of the lenses on the percentage of non-flat ratings and on the percentage of distinctly true to life ratings. There was one outlier. The Konica Hexanon 57 f1.4, which has a very similar optical construction to the Focklander, which scored quite well in this test, punched much below its weight. And I wondered why. When I looked at it closely, I noticed that it has a distinct brown tint. Then I had a look, and it turns out that this lens, like many lenses introduced in the 1960s, have thoriated glass elements in them, which means it is a radioactive lens. One of the effects of the alpha radiation emitted by the glass is it turns brown over time. So the dispersion this lens creates is not full spectrum. Some of the visible spectrum is absorbed by the glass itself, and the dispersion is only partial. which explains why the images it makes are perceived as less poppy than the optical design suggests. To compare the autochinon that was made at about the same time does not display this browning in the glass. And indeed, it scored much higher than the Konica. Excluding the Konica Hexanon 57mm from the model, obtained very good fits between dispersion score and all three ways of describing the poppiness of a lens according to the survey. The mean rating, the percentage of responses that were higher than 2, which means the rendering is at least mildly poppy, and the percentage of ratings of 4 or 5, which is distinctly poppy or true to life. The R squares obtained, which describe the quality of fit, were around 0.99 for each of those variables. According to this model, the threshold value for a portrayal that is more poppy than flat is about 0.11, while the threshold value for making the rendering look distinctly poppy to more than half the population is around 0.14. So if you like your images to look true to life and poppy with a good sense of depth, you should really look for lenses with a dispersion score exceeding 0.14 or so. Next, I will give you some example of lenses with a higher dispersion score, and I will refer to lenses that I own. My favorite lens currently, the Hypoximera 28mm 1.4, gets a score of 0.27. The Nikon 35mm f1.4G, the old one for the f-mount, gets a score of 0.30. The newer Nikon Z 35mm f1.4, the one filming me now, gets a score of only 0.18, but it is higher than that threshold score, and indeed it makes some nice and lifelike images. The Jupiter 9, the Soviet copy of the Zeiss Sona 85mm f2, gets a score of 0.29. The Falklander 35mm f1.5 vintage version gets a score of 0.33. And the Sirui 85mm f1.4, which is another modern lens I recently acquired for my mirrorless camera, gets a score of 0.14, which is more or less the threshold between what would be considered poppy and what would be considered flat. But it is still slightly nicer than other 85 or so millimeter lenses. Just to compare, the Carl Zeiss Jena 135 f3.5, which is another longer lens I like, gets a score of 0.25, which matches my impression that it is a very true-to-life portrait lens. On the other hand, the Sigma 85mm f1.4 art made for DSLRs, the older version, has a dispersion score of 0. The new one made for mirrorless cameras has a dispersion score of minus 0.07, and the lowest dispersion score of all the lenses I looked at is the new Nikon Z 35mm f1.2 with a dispersion score of minus 0.12. This model I developed is a crude simplification. The truth is much more complex than this, because not all low dispersion glass types are the same. Some of them have higher Abbe numbers, so they suppress dispersion more than others. This model also assumes that there's a relation between complex groups and high refractive index elements, but this is not always true. Sometimes there are single elements that constitute a group on their own that are made of high refractive index glass, which will affect the accuracy of this model. In addition, the placement of ED elements and the high refractive index elements may affect the rendering. For example, if you have a low dispersion cluster at the front of the lens and a high refractive cluster towards the rear of the lens, the rendering will be poppier than expected. As Albert Einstein once said, all models are wrong, but some of them are useful. So I hope you find this new interpretation of lens design useful to you. If you have anything to remark or say about the content of this video, please let me know in the comment section. And if you liked what you saw and wish to support this channel, please buy me a coffee. There is a link in the description below. It's a nice gesture between gentlemen. So thank you for watching, and see you again soon.